Thank you very much, Giovanni, for the invitation, a chance to tell you about our work. I'm Sara Majetich. This work was done with grad students Brad Parks and Hao Chen and undergraduate So-Young Jun. And here we have a superparamagnetic tunnel junction, which looks a lot like a regular tunnel junction. Everything I'll tell you about today uses COFIB with an MgO tunnel barrier. But what makes it different is that instead of having a constant resistance associated with the parallel or anti-parallel state, we have something that fluctuates between these states stochastically, and we have control electrically, either through a voltage or through a current that favors one state or another. So again, I want to start by saying what these tunnel junctions are and a little bit about the applications. Want to say a little bit about two of the applications that we've demonstrated, but then say more about the most intriguing application, which would be use in probabilistic computing. So I want to explain how that works and show some experimental results and finish up with a discussion of future work. So as I said earlier, a superparamagnetic tunnel junction is a regular tunnel junction where the free layer is superparamagnetic. And by that, I don't mean the strictest form of superparamagnetism of an ellipsoidal particle with uniaxial anisotropy. I'm just referring to something that has a low energy barrier between states. And so you can see it switches between parallel and anti-parallel magnetization, depending on whether you're looking at the tunnel current or flip that for the resistance, but two states, and you can change the preference or the speed of the fluctuations basically by changing the height of the tunnel barrier. So normally for memory, you would want high thermal stability and a big tunnel barrier with this thermal stability parameter delta on the order of 60 to 80. But for probabilistic applications, you want this as small as possible. So we haven't gotten down to 1 kT, but we've gotten down to a few kT. One thing that we find that's interesting, I don't have time to go into, but in many of the cases when you get down to very low energy barriers, you really are losing the uniaxial anisotropy. And so instead of switching between magnetization up and down, you're just tilting the angle back and forth. But for the probabilistic applications, what you care about is how quickly it fluctuates back and forth and the ability to tune between one state and another. So here's an example where we started in this project looking at perpendicularly magnetized tunnel junction. And if you were to measure the tunnel magnetoresistance as you sweep the field, you get this black curve and see deterministic switching, and then it comes back and switches to the low resistance state again. But if you sit at a particular field and measure the resistance as a function of time in this hysteretic, apparently hysteretic region, what you see is that it's actually fluctuating stochastically. And at 130 Ersteds, it's mostly in the anti-parallel state, and down at 113 Ersteds, it's mostly in the parallel state. And you can switch this, or you can tune this with small changes in an applied magnetic field. But of course, if we look at this and we look at the time averages, we get this red curve here. And this is what we'll call the sigmoid curve. This is what you want to be able to tune. But in particular, you want to be able to tune it not just with an external magnetic field, but with a voltage or a current, because this was what would be needed in order to make devices and have high densities of superparamagnetic tunnel junctions. So this is what we're looking for. Fortunately, in spintronics, there's lots of options for how to control magnetization. We could use, for perpendicular magnetization, we could use voltage-controlled magnetic anisotropy. And in general, if we've got a conducting material, we can use spin transfer torque or spin orbit torque. We've used all three in our devices. Here's an example where we use spin orbit torque to switch devices, and We've looked at the state switching or not switching with our conductive atomic force microscope. So we can do this with devices as small as 20 nanometers. So it's certainly possible to make very small devices and take advantage of the superparamagnetism in the free layers. So I'd like to say a little bit now about some of the applications. An obvious one would be random number generators, which we need more and more of for encryption of our data, and hardware random number generators are true or can be true random number generators, whereas the software ones have some artifacts that are introduced. And with our superparamagnetic MTJs, we can make them much smaller than the ring resonators that are now used with CMOS. You could do analog multiplication, which by itself, independent of CMOS, might not have tremendous advantages, but used together with CMOS could reduce the power consumption. This is something that spintronics would naturally do better. And then the different types of logic gates, either for decryption or for encryption. So there's a lot that can be done with these superparamagnetic MTJs. And then there's more complex problems that can be solved, again, using the hardware, not just software. And in general, there's interest in low energy computing or sensors, a lot of devices where speed is not the most important thing and power consumption is significant. There are trade-offs where these probabilistic devices could find niche applications. So let me just explain two of them and some of the differences in the qualities in terms of the physics that are desirable or undesirable depending on what you want to do. So the first would be a voltage-controlled magnetic anisotropy random number generator. So here the advantage is very low power. And we can see that our resistance of our device, we can see it naturally flipping back and forth, and these little glitches here, that's just electronics, that's not the physics here. But we see it switching back and forth at minus 0.4 volts, and we go to minus 1 volt, and it's switching back and forth much more rapidly. So if you want to tune the frequency, you could make a very fast random number generator. This is actually one of our earliest devices, so it's very slow. We can now get down to hundreds of nanoseconds, so we can make them fast. It's really limited by our capture electronics. But one feature that we observe in these sorts of devices is that as we tune the retention time, the average time between switching events, we're not having a big effect on the preference for the parallel or the anti-parallel state. And that is very characteristic of these perpendicular devices. And so for logic gate applications where you want to have a preference for parallel or anti-parallel, we don't think that these are as good. And so we work preferentially with in-plane magnetization devices. And here's an example showing analog multiplication, where if you look at the inputs into a CMOS AND gate and you average the signal over time, the output is the product of the time average of the output is the product of the time averages of the inputs. And when we look at how quickly you could do this multiplication, depends on how fast your individual devices are to begin with. And so the faster the devices are, the faster you're going to get a good estimate with low error. So typically, if you've got, say, 100 switching events, you get reasonable statistics. So one of the issues also that comes up is when we look at our resistance as a function of bias voltage, we see that the telegraphing region, this blue area in here, is offset by a couple of tenths of a volt. And if you're really thinking about low power application, you don't want that to have that big voltage offset or modest voltage offset. You would rather have it very close to zero and still get the tunability that's shown with this red sigmoid curve. And so one of the things that we did was to go to smaller dots and circular dots. And so same diameter, but circular. It's based on the magnetostatic offset, no external field, but an internal magnetostatic field. We do have an offset, but if you cancel that, and it's just a 7 Ørsted field, then you can shift this to around 0. So you could, ideally, you could have these devices that are free-running superparamagnets where you don't have to have, well, you only need enough power to measure the resistance. So this could be very low-power devices. And here again, we've speeded them up. So we've gone from milliseconds now to microseconds and even below. And we see that as you tune the voltage over a relatively small range, you go from favoring the parallel state to favoring the anti-parallel state. So we get the full sigmoid curve. And if we look in more detail, here is our sigmoid curve for the data, the last slide. And that looks very similar to what Keremchand Sari and his group have been looking at with the simulations of devices. So we get really, full switching over a few tenths of a volt. We also look at the statistics of our events to see, are we looking at Arrhenius law behavior, and over the timescales that we're looking down to a few hundred nanoseconds, we are, when you go really small, you start to see deviations, and that just has to do with our binning electronics, not the physics. So we can make these devices, and now it's a question of what can we do with them. So here's an SEM image of different sizes and shapes and orientations. So we can get down to about 20 nanometers with e-beam lithography. And these days, a lot of what we're making, especially for the logic gates, we hardwired the devices because we want to protect the sidewalls from oxidation and be able to freely connect a few to each other. We're looking not at large scale integration at this stage. We're looking at 2 and 3 devices in tandem for our proof of concept demonstration. So in these devices, these little flower shaped patterns in the SEM have 4 electrodes connected to the top of the tunnel junction and 4 connected to the bottom. So lots of flexibility there. But if you read some of the papers where theorists and the simulation people have talked about interconnecting 600 devices with 600 other devices, that presents a real wiring challenge. I don't think that that's going to happen. I think we could get 6, 8 devices, but beyond that, it's going to be very complicated. So looking at probabilistic computing, let's consider the difference between probabilistic and quantum computing. With a qubit, you have quantum mechanical entanglement. And so this is very powerful. Lots of people are excited about this and trying to make this happen. You could do an infinite number of computations at the same time, but it requires the ability to make this coherent superposition that evolves over time, and there's a question of how long it retains its coherence. There's also real issues, certainly with the superconducting qubits, of the ability to switch from isolated to connected. So there's still a lot of physics to be worked out there, even though it's a very exciting area. In contrast, I would say the probabilistic bits, or P bits, as Supriya Datta has designated them, are very close to being reality and being something that we could take advantage of. They would work at room temperature, so you wouldn't need liquid helium. And I think the technology is there, or is very close to being there. So a lot of, not everything, but a lot of things that can be done with quantum computing can also be done with probabilistic computing. And so since we all like Schrödinger's cat to explain probabilities, we can think about quantum computing where you've got Schrödinger's cat that is in a superposition of an alive and a dead state, and you don't really know until you measure. And if you measure, you destroy that coherence. In contrast, say Boltzmann has a cat too, and Boltzmann likes probabilistic computing. In this case, you can set up with your sigmoid curve the relative probability that the cat is in the alive state or the dead state. But when you measure it, you don't destroy that probability that is programmed in, that stays the same. You can adjust the feedback, but you're basically, with probabilistic computing, you're doing the measurement again and again and again and looking at the statistics to get the information. So if you wanted to, say, multiply some numbers or represent some numbers, you would need a superparamagnetic tunnel junction for each bit of information, but you could program that independently with the relative probabilities of alive or dead, or basically the point on the sigmoid curve, and then look at representing different numbers. And so, if you're doing, for example, integer factorization, this would be one way that you could look at the number 35, 5 times 7, weighting it by the digital bits. But in order to do a calculation, you would have to be measuring enough times to get good statistics to reflect these probabilities. And basically what is being done with hardware in probabilistic computing is that you're solving a Monte Carlo simulation of an Ising model. So you could treat it as having this exchange term and then an external bias term. And Monte Carlo people have been doing this computationally for years. The difference is with probabilistic computing is that you can minimize the energy through a hardware kind of problem. So here, if we contrast the way you would do it with Monte Carlo simulation and the hardware, typically you set up your conditions and then you select a spin and you look at the interaction with all the other spins, and then you have a probability that you flip that spin independent of the others, and then you march along to the other spins and continue this. With the hardware version, you're doing this all at the same time. All of the nanomagnets are interacting with each other. And so here's one example of comparing spin up and spin down. If we have just two spins and they aren't coupled to each other, and we look at the probability and say spin up corresponds to 1, spin down corresponds to 0, we would see these pairs of probabilities of spin 1 and spin 2 all be the same. So it's just random. But if we have some sort of dipolar or exchange sort of coupling, then you can favor the states, get higher probabilities of finding them with opposite spin orientations. And so in this case, we would say this is a not operation. The state of spin A is not of the state of spin B. So again, simulations have been done by Karamchandari and Supriya Datta. We've been looking at more of the hardware version of this with our hardwired MTJs. And so here, in order to get fast dynamics, we have, say, 2 or 3 of them. They're hooked up together to our red Pitaya boards so that we can measure down to hundreds of nanoseconds. And we can correlate them so we know the state of one at the same time as the state of the other. So we come back to what we were looking at earlier with our lifetimes in the time between switching events in the parallel state or in the anti-parallel state, which we can tune with an applied voltage. And we define what's called a half point, where 50% of the time the device is in the parallel state and 50% of the time in the anti-parallel state. And we can relate that to the sigmoid curve that we have for a particular device. So we go through and we characterize each of our devices. And then when we do this, if we want to couple them together, we have to decide not to let them just free run, but we want to tune them so that they can behave like a logic gate. And that would be, if we move away from what we call the basic bias, which is at this 50-50 point or half point, If we want to favor the anti-parallel state, we add an additional voltage to shift to the right. If we want to favor the parallel state, we reduce the voltage and shift to the left. So this is the concept of all the coupling. And so here is some data that we've got for two devices. In blue is the first device, and in red, the second device. On top, they're free running. They're not coupled to each other. We see the blue device is in a situation that favors the parallel state. The red is in a condition that favors the anti-parallel, but they're really not correlated with one another until we hook them up and using this dipolar, well, not dipolar coupling, using the feedback that should give the knot arrangement. And in fact, we see that 95% of the time, the state of device 2 is the knot of the state of device 1. So the knot gate is quite straightforward. It's almost deterministic. However, the big challenge for probabilistic computing is that the other gates are not anywhere near as close to being as deterministic. It's a much more statistical process, and it has to do with the energetic preference. And so let me, sorry. Let me explain for my dog how this works. So he wants to get Schrödinger's cat, sorry. So getting back to deterministic behavior, when we think of a logic gate and a truth table, that we think if we have inputs A and B, that the output C is 100% going to be 0 if we know that the input A is 0 and B is equal to 1. But if you've got a probabilistic gate, that's not true, that you're going to have, again, 8 different microstates, and each of them is going to be equally likely in the random case if they're not coupling. Yet only 4 of these microstates are consistent with the AND gate truth table. So the art of connecting these weights and shifting the set points of the different superparamagnetic tunnel junctions is to try to energetically favor the states that are consistent with a particular logic gate. So here's some data that we were able to do this, and you see that we can definitely shift away from the random case, but we don't get the level of the 95% preference that we did with the NOT gate. And that's just not going to happen if you look at the theory behind this, but you do see a preference. So one of the issues with working with probabilistic logic gates like this is figuring out how long do you have to average and how much of a difference is going to be meaningful in terms of the preference for particular states. What we have found is that comparison of these pairwise microstates, looking at the relative probabilities, is a very reliable guide that we do get a preference. We're always going to see that, say, the state with all of them 0 is going to have a higher probability than the state with A and B is equal to 0, but see the output being 1, which is inconsistent with the AND gate truth table. So that's the way that we analyze and compare the results for different scenarios and different levels of the feedback. And really what you're doing is you're looking at an energetic picture of the preference for different microstates. So if you had the ideal AND gate, it would be these blue states would be infinitely high in energy, and that's not what we have in a probabilistic scenario. Oops, go back. Oops, sorry. But there is a preference. So the red states are these low energy states, and then what people are doing in decryption is to pin one of the outputs, whoops, and effectively you're changing the relative energies. You can lower the ones that say have state C, the output equal to 0, or relatively raise the states of the probabilities of the microstates that have C is equal to 1. And you're perturbing basically these Boltzmann relations that are involved in calculating the relative probabilities. So that's where we are. And I think since people have been very patient, I don't want to go into a huge amount more details, but if people are interested, I'm happy to talk more with you about that. So we've seen ways to design logic gates, probabilistic logic gates based on superparamagnetic tunnel junctions. They work, they have some issues. There are some choices in design that make some types of tunnel junctions better than others for particular applications. So I'd like to thank the NSF who funded the work and people who supplied us with samples and computational help. So thank you very much.